Okay, let me show you one thing here. Minimize this. And I'm going to go, let's see, I'm going to have to stop the share to do that and share my browser instead. Uh, Here, share this one. Here's my browser. And here's the EXAM5 page in CHEM212. If you go down, um, I found one for IR spectroscopy video, and I might as well click on that. It takes you out to the YouTube location for the video, and you have to sit through commercial.
My daughter is being treated for leukemia. It's hard. Techniques, spectroscopy and spectrometry.
You have to get past the guy's British accent, but they're excellent videos. I mean, he just condenses it down into, like, this is only 10 minutes. The NMR is like 20 minutes, and it just pulls everything together. It's impressive. It would take a little bit of study, yeah, and looking at the review video that I have for this material, I think that'll help. Once you've covered that, then I think you'll be ready for it. So you could probably get 4 and 5 done just like that. And then since 6 is canceled, all you have to do is show up or Zoom in if you want. You don't even have to show up for class. You, yeah, because we don't. I'm having to throw out the last lab, so you could just Zoom in if you want to save some gas, and I'll just do an intro for polymers, and that'll be it. Okay, so let's see. Click on that link, and we go down. This other one is, let's see. Here's the review. It looks just like you normally would see. Maybe I was able to do it because there was only one student left in the 212 class. I had 3 and 211, and then 2 of them decided they didn't need the second. So I only had 1 student. So we took all the time we wanted. But if we go, I'm going to try to introduce some of the ways that this guy, I forget his name, but he's got a web page, a YouTube channel called Chemistry, and he that just dozens of excellent videos pulling things together. I've started incorporating some of them into my other courses, so they'll be ready for the fall. Okay. That's just a taste. All right. So that's what I wanted to show you, and now we'll get into the PowerPoints. There we go. Let's make a slideshow. That's also his video has also helped me focus my attention on stuff that's important. So there's a lot of stuff in this series of slides that are interesting and useful, but not essential. So when I come to those, I'm going to try to just kind of gloss over them and not waste your time with it. Nuclear magnetic resonance. All right. Let's see, that's just outline. This is the most powerful tool that organic chemists have for determining the structure of a molecule. We get information from IR, we get information from mass spectrometry. But if you really want to, if you want to maximize the impact of the technique, go to NMR. NMR stands for nuclear magnetic resonance. And I like, in all my courses, I like to break down words and names because otherwise, why bother? When we say resonance, and we know it's due to some type, we are saying it's due to some type of radiation. In this case, it's radio waves. And the particular species, maybe a whole molecule, maybe parts of a molecule, they tend to resonate at certain frequencies. That's why we can stand here and there are dozens, if not hundreds, of frequencies of radiation that are passing through our bodies right now. Some of them natural, some of them man-made, and they don't affect our bodies because the molecules, the atoms inside our body do not resonate at those frequencies. So they just pass through without effect. That's why we can pick up, in most cases, we can pick up a cell phone signal through the walls because the signal doesn't resonate with the material in the building. Magnetic resonance, magnetic refers to the fact that when we're investigating a molecule, it's under a very, very, very strong magnetic field. And I'm going to explain why we need that. And the nuclear part means that we're applying this magnetic field to the nucleus of atoms in the molecule, and then also applying a radio signal or a microwave, I can't remember which it is, I think it's radio, to resonate those nuclei. So that's what NMR stands for. And NMR, the output from a nuclear magnetic resonance investigation is a spectrum. It has peaks. Whereas what we normally are more intimately associated with this technique is, in the medical sense, magnetic resonance imaging. Now, when it first came out, this came first. And then the medical profession got hold of it and said, maybe we can use that to our advantage, investigate. We already had x-rays and CAT scans, and that requires x-ray signal attenuation by hard parts of your body, like bones. Right? But if we want to investigate soft tissues, then this is the way you go. And it used to be called nuclear magnetic resonance imaging. And the output here is an image. But this was dropped because when this technique came out in during the Cold War, anything that said nuclear in front of it, everybody just freaked. That was the late 50s and 60s. Everybody headed for the bomb shelters. But it's essentially the same physics that are being applied to the molecules, whether they're in a sample, in a chemistry lab, or whether you're in that torture chamber, that big toroid, it's banging away at you. Every time it bangs, I think it's taking a picture, and it takes a picture like this, and then pieces it together into a three-dimensional. Okay, let me see. I might have stolen my thunder. What we can gather from nuclear magnetic resonance is the number and types of either hydrogen atoms or carbon atoms in a molecule. And when we say types, they are distinct from one another in the spectrum itself. And you can see that in the spectrum. And the types of these hydrogen or carbon atoms depend upon their connectivity with other atoms in the molecule. That's essential to determining the structure, because if you know how the spectrum tells you how the hydrogen and carbon atoms are connected with one another, then you can work that out into a structure. Because if you have, I think the example I used earlier was the exact same molecular formula for ethanol is also dimethyl ether, but they're different connectivity. These are isomers. They're structural isomers, and each one of these will produce a different nuclear magnetic resonance spectrum. And you can work your way back from the spectrum to this, because you're going to be given the molecular formula. That's essential. And then you look at the spectrum and see how that makes the connections. IR spectrum doesn't give you much about connectivity. It does tell you a little bit about the types of functional groups that are in the molecule. So that's helpful. And UV vis is not very good at any of those. It's UV vis spectroscopy is very useful for quantifying concentrations of molecules. That's why we talked about the lambda max. We look for the peak that is the highest absorbance, and that's used for to calibrate your spectrometer with different concentrations of known of the known material, and then you take your unknown and you can say how much is in the sample. So UV vis is best used for quantifying concentrations. IR can tell you a little bit about the functional groups, but NMR, that's where you get your structure. So infrared radiation obviously is in infrared range of electromagnetic spectrum. UV vis is ultraviolet or visible. Nuclear magnetic resonance uses radio waves. And it's going to make more sense when I describe the technique. So let's just gloss over that for now. I don't think this is really, it's interesting information, but it's not essential. All right, this is an artist rendition of what an NMR device looks like. You've got superconducting magnets. That's required for very, very strong magnetic fields. I think MRIs will be in the neighborhood of like 2, 3, up to 5 Teslas, right, which is pretty strong. It's strong enough that they have to determine if you got any metal in your body. What type of metal it is. What's that? Oh, I didn't see that. Uh-huh.
He went in there, had a net. It sucked him in there and killed him.
Ooh. It must have strangled him, huh? I guess once you get in there, then the magnetic field is swirling and it just starts twisting that necklace. Oh. Yeah. You ever see that movie, The One, with Jet Li? Yeah. They go to a hospital, and one of the characters, Jet Li plays multiple characters. One of the characters he plays, they put him in an MRI machine. And then he gets attacked with the other character that he plays. And he pulls out a gun, and the magnet sucks the gun out of his hand. So your sample goes down in this very strong magnetic field, the superconducting magnet, and then you blast it with radio waves, and it produces a spectrum with various peaks. Let's see. Get that out of my way. Come on. There we go. Why didn't you show the bottom one? There it is. It just took a while to render it. Now, the solvent that you use is important, especially if you're going to use, there are basically two types of NMR that are popular that are used. One is hydrogen NMR, and the other is carbon-13 NMR. So in one, you're looking at just the hydrogens in your molecule, their connectivity, and the other, you're looking at carbons. And the reason you have to use carbon-13 rather than hydrogen is NMR will not respond to nuclei that have even numbers of protons and neutrons. So if you have, say, helium, which has 2 protons and 2 neutrons, that will not produce an NMR signal. It has to be odd, either odd protons or odd neutrons or both. So hydrogen's good because it only has 1 and 1 here. And carbon-13 has to be because it's 6 here, but it's 13 there. That means 7 neutrons, odd number of neutrons, so it'll give you a signal. But the solvent, we typically use a deuterated solvent. In this case, let's see. Trichloromethane. That's what we're after, trichloromethane. But we have to use a deuterated solvent. Now, deuterium is going to give you a signal too, right? Because it's like this. It has an odd number of protons, odd number of neutrons, but it's going to give you a signal in a different part of the spectrum, so you can cancel that out, right? You'll know where it is. It's not going to interfere. If we used a normal trichloromethane, then you would have a signal from that superimposed on one of your hydrogen signals. So we don't want to use that one. Now, you can still get some, it's not perfect. The deuterated trichloromethane is not perfect. It will have a few atoms in there that still have protium in them. But hopefully, if it's a good quality solvent, it's not going to be significantly impact your outcomes, the spectrum. Okay. And the radio waves are irradiated with short pulses of the radiation. And I'm going to try to explain in just a few minutes why that works. Okay. Okay, now we're getting into it. We have this very, very high external magnetic field. Now, the reason you want that is because nuclei can be visualized as little bar magnets. They have a spin. I mean, each proton, each neutron has a spin. Remember when you were doing electronic configurations, the last of the four terms in the definition was spin. You had the principal quantum number, you had the L number, the M sub L, and the M sub S, which is the spin. Well, nucleons, protons and neutrons also have spin. So what you do with a strong magnetic field is you cause those neutrons and protons to line up with the field. It has to be a very strong field, probably because they're so massive. It wouldn't take such a strong field for electrons. And the so once you have the let's see, let's put it on an energy scale. Once you line up these, let's see, you have once you put them in the magnetic field, they're all lined up with the same spin. Okay. And when you add energy to them, right, you have these radio frequencies in here, then you cause them to flip. They'll absorb the energy and they'll flip to a higher energy state. Now, it may be just one of them, right? Or it may be two or maybe three, depending on how many are in. For hydrogen, it's only going to be one. So let's simplify it. Let's say it's a hydrogen NMR. We just got one proton doing that. And then it does this when you hit it with radiation. Okay. Now the radiation is pulsed. So between pulses, I think the generator, the pulse generator, acts as a receiver also. So it pulses the signal and then it listens. And it listens for the output. And when this one relaxes, it's in this strong magnetic field. And the only reason it flipped opposite to the magnetic field, which the magnetic field is this way, right? This is the magnetic field. The only reason it flipped is because we added energy to it, caused it to flip. And then when it returns, when it relaxes, it's going to give up a signal. Okay? When it relaxes, it gives up that energy. And that's what we detect. Now, if all the hydrogens were exactly the same in that molecule, then you'd only get a single signal return here. But they're not all the same. The environment in which each one finds itself changes how it responds. Okay. Let's see. And this is called the chemical shift. So the environment depends on what's happening with the magnetic field in the immediate vicinity of the atom. So let's take this one like that. So that would be that's be an aldehyde, and you got these hydrogens here are connected to this carbon. Over here, they're connected to this carbon, but that oxygen has unpaired electrons. And they're going to modify the effect of the magnetic field on this hydrogen because they're so close to it. Whereas these are different. These are unique hydrogens. That one's a different hydrogen. All of these are the same with respect to how they respond. So what that means is this hydrogen is shielded. with these electron cloud. And that means if we want it to flip from this spin to that spin, it takes more energy. So we have to hit it with high, it's going to absorb more energy, and when it relaxes, it gives up a response that's said to be shifted, right, based upon its shielding. It's more shielded, so it gives up a different energy. That's how we can tell one hydrogen from the other, depending on its environment. Okay, so here are your little bar magnets. They're in a strong magnetic field, yep. Without being subjected to that magnetic field, you're not going to get them to absorb radio frequency. Any radiation, they won't absorb. Sometimes they're called alpha spin state, beta spin state. When you see those terms, alpha is the lower energy and beta is the higher energy state. So this is what they look like when they're on the left. They're not in the magnetic field on the right. When you put them in the magnetic field, then you get the you get them to line up with the magnetic field, and then when you hit them with energy, you end up with the higher energy state. Okay. All right, this is one of those cases I'm going to kind of gloss over it because I've already talked about it for one thing. And so I think what we're showing here is several different hydrogen atoms. And only one of them flipped. So it gives, and it flipped with a certain amount of energy depending on its environment. And that gives you a chemical shift. Okay. All right, I've already covered that material. All right, protons are not the only ones that can be investigated this way. I mentioned earlier we can use carbon-13. The problem with carbon-13 is that all molecules will have some carbon-13 in them. Most of them will be carbon-12. Carbon-12 is, well, carbon-13 is about 1.1% of all the carbons. So you're going to have a weaker signal because the carbon-12 will not respond. That's why when we look at NMR spectroscopy, we typically gravitate toward protons rather than carbon atoms. We only use carbon when it has the potential for giving information that's protons. There may be questions about, and the carbon-13 NMR might be a tiebreaker. Okay. And I've already talked about that. Just there it is in black and white. Other nuclei can be used, right? So if you're a graduate student and your professor wants to work on a different atom, then you say yes, sir, and go ahead. Or yes, ma'am, and go ahead. Nitrogen 14, right, would have an odd number of protons and neutrons. 15 would have an odd number of protons only, because it would take 7 protons and 8 neutrons, so you're only going to use the protons in that situation. Oxygen 17, fluorine 19, phosphorus 31. Those are possibilities that have been used for NMR spectroscopy. And I can see where they would be valuable if your molecular formula has determined that there are nitrogens, there are oxygens, there are fluorines or phosphorus in your molecule. And in that case, you may want to go to another type of spectroscopy, maybe IR or mass spec, to help work through the structure for these non-carbon atoms. Okay. Now that's a good point. I think I made the point, but it's good to be, if all the hydrogens were in the same magnetic environment, right, then you'd get one signal. That's it. And it wouldn't help you at all. But since the environment determines how they respond to the radio pulses, then we can see differences, and that gives you a shift. All right. Now, determining chemically distinct hydrogens and carbons in an atom is an important technique. The different peaks that you get in the spectrum, right, whether you get one here or here, I'm not making them sharp enough. They're very sharp. Right. Each one of these peaks represents a different, let's restrict ourselves to hydrogen NMR. This is a different hydrogen for each one of these peaks. Now you're going to have 0 here, and then you're going to shift this way, bigger numbers. This is known as, any place in here is known as shift would be upfield or downfield. So upfield means they're more shielded, downfield means they're less shielded. And this one, this 0 point is determined by a reference standard. And that's usually, not always, but very often, is silicon, silicon tetramethane. Okay. And the main reason for that is that carbon is more electronegative than silicon. So you're going to get a dipole around here, which balances the whole molecule. That's one of the reasons. So that gives you a formal charge for the carbons of negative. Right? And that gives you a uniform shielding for all of the hydrogens to be exactly the same. So you get a single peak right here. And the nature of this molecule says that there's nothing that's going to be shifted downfield from this one. So that's your 0 point. The little bit of this in your sample will give you a peak right here. Most NMRs are programmed, the computers are programmed to blank that one out. Sometimes they'll leave it, sometimes they'll get rid of it, but they'll always show you the 0 point, and that's due to usually this molecule. Okay, so once you've got the 0 point, then all the downfield, the upfield shifts are referenced properly, so you can compare one spectrum with another. Okay, so here we've got, let's see, this is a challenge to see if I can name that molecule. Priorities. That's a carboxylic acid, right? So, and it's also a, it's got an ine. So it'd be like, let's see, the carboxylic would be 1, 2 would be iron. I'm not going to stretch my brain on that one. Oh, there's the name, right? I'll just read the slide. propanoic. It's a mouthful. Propanoic acid. Okay, so there's our reference peak that's actually shown in this one. That's oh, okay, TMS. I knew it had an acronym. TMS is tetramethylsilane. Methane, where do they get that name? CH4 is methane, right? SiH4 is silane. And this is tetramethylsilane, TMS. Okay, so there's your reference peak. And then you get two peaks here. The reason you only get two is because there are only two hydrogens, but they're in different environments, right? The one that's closest to the oxygen is more shielded. So it's shifted way, way downfield, about 11.2. And the units of measure here are parts per million. Now, I'm sure there's a way to calculate that, but it's not important for us to know how they calculate ppm. The less shielded one, the upfield, downfield. Upfield is the carboxylic hydrogen, and the let me see if I'm getting that right. Upfield, downfield. Downfield is to the left. Upfield is to the right. So that one hydrogen attached to the triple bond is going to be less shielded. I think that has to do with effective electronegativity. Remember when we were talking early on, triple bonds have a higher effective electronegativity than double bonds than single bonds. So what they tend to do is draw electron density away from their surroundings. And that deshields that hydrogen, which causes it to be 3 ppm versus the extra shielding that's provided by the carboxylic. Both the alcoholic oxygen and the carbonyl oxygen tend to further shield that hydrogen. Excuse me. Okay. They're in different chemical environments. All right. That doesn't tell me anything new. All right. What about 3-bromopropanone? How many unique hydrogens do you have in that molecule? Well, if we look at the structure, we see there's one over there by the triple bond, and then the hydrogens on the carbon are identical. So we have two unique types of hydrogens. So we should expect two signals, right? Now we haven't talked about the effect of nearby hydrogens, and we're choosing these molecules for that reason, because those a hydrogen has no other hydrogens around it on adjacent carbons, and the carbon attached to the bromine only has hydrogens there, and those are identical hydrogens, and there are no hydrogens attached to the other carbon next door to it. So there's no, we don't complicate the spectrum with nearby hydrogens. We're going to talk about that in just a minute, but this, for now, we find that the more shielded one is the one close to the bromine, because bromine has 3 lone pairs of electrons. So those B hydrogens are more shielded. They're shifted downfield. I think downfield. And the ion hydrogen is upfield from that. Okay. Considering this molecule, which dichloroacetic acid. which one of these spectra should you expect to be, which one of the spectrums should represent this one? How many unique hydrogens do we have in this one? You've got one on the carboxylic, and you got one attached to a carbon and two chlorines. They should be different. Right, so you're going to have the one on the left, the spectrum on the left should be the one associated with that molecule. Now, we're not saying which one is the more shielded, right? Which one would you expect to be the more shielded one? The hydrogen on the left or the hydrogen on the right? I think the one on the left should be more shielded because each chlorine has 3 lone pairs, right? And they're all the same carbon attached to the hydrogen, whereas the hydrogen on the right is only attached to one oxygen, and it's receiving some shielding from that one, the 2 lone pairs, but the other one is a carbon away from it, the carbonyl oxygen. So I think the more downfield is the hydrogen attached to the carbon with chlorines. It doesn't say in the author doesn't tell us, but okay. I think what Dr. Carty is trying to do here is to help us work through the uniqueness of hydrogens in the molecules. So if we have this molecule, which is 1, 2, 3, 4, 5, 6, 7, this heptane, the hydrogens there's a plane of symmetry through carbon 4, right? So the hydrogens on carbon 4 are going to be unique. The hydrogens on 3 and 5 are going to be the same. The hydrogens on 2 and 6 will be the same, and 1 and 7 will be the same. So how many unique hydrogens do we have here? 1, 2, 3, 4. We have 4 unique hydrogens in that molecule. And that means we should have 4 peaks. Now, unfortunately, we haven't studied yet the effect of nearby hydrogens on those peaks that we're going to get with a concept called splitting. Right? We are going to get there, though. Now, this is a different molecule. Right now, we've got double bonds involved. How many distinct types of protons are there in the following molecule? All right. Does a molecule have a plane of symmetry? 1, 2, 3, 4, 5, 6, 7, 8. Yes, between 4 and 5, carbons 4 and 5, there should be a plane of symmetry. Which protons can exchange their locations? Well, let's just say which ones have the same environment. How about that? So we're going to find that the protons on the end of the molecule are the same. The second one's over, third one's over, and the fourth one's over. So we have 4 unique hydrogens environments in this molecule, 4 sets of protons. So we should have 4 peaks in a proton NMR. All right, what the author is trying to do here is to give you a method for determining uniqueness of the hydrogens. And he's doing this X substitutions. I guess it would work, but I think there's a simpler way, right? If you have something like you just look at what are these hydrogens attached to, and what's their immediate environment? and you look at the connections to the atoms that the hydrogens are attached to. So let's just make something up. Say we have, well, I don't know, say a double bond, and then you have like this. Let's just put a hydrogen there. Let's say we have this, this. All right. So each one of these is going to have 2 hydrogens. Like that. This one's going to have 3 hydrogens. Okay. Each one of these hydrogens is equivalent, right? So that's going to be one type. This one has a methyl group on one side and a carbon with 2 hydrogens on this side. This is going to be unique. This one has 2 on that side and 2 on that side. That's going to be unique. This one has a double bond on that side. It's unique. And this one's unique. Wait a minute. We've got 1, 2, 3. We're going to have hydrogen here and hydrogen here. So is this the same as that? Well, no, because this one has an oxygen attached. That's unique. That's unique. 1, 2, 3, 4, 5, 6. We should have 7 peaks out of this one. And I think if you look at that chemistorian video, I think it'll clear up a whole lot of this stuff and make it really much simpler. Okay. All right. Abe wants us to use the technique to determine if chloroethene, how many chemically distinct hydrogens are there in this molecule? Right. Well, let's see if we can do it before we try his method. We have this one here. We have this hydrogen and a chlorine, right? Okay. So this hydrogen is unique. These hydrogens are unique. We only have 2 distinct hydrogens in this molecule. And that we did that a whole lot quicker than, let's see, because A and B are diastereomers, the 2 protons that were replaced are distinct, A and B. So he's saying we have 3 distinct protons in the original molecule. A and B are not the same. Oh, no, they're not. Okay, I see his point. Okay, let's try it this way. There's a hydrogen, there's a chlorine, these hydrogens. All right, what environment does this one experience? Since this molecule is locked in a plane, then this one is experiencing not only that double bond, but some of this chlorine on that side. This one doesn't have that on that side. So these are unique hydrogens, all 3 of them. Okay, does that make sense? Okay. So we should get 3 peaks out of this molecule. Okay, now we're switching gears on us. Axial and equatorial hydrogens interconvert, right? So you're only going to get a single peak out of those. If you have a chair conformation for a cyclohexane, then those 2 hydrogens are indistinguishable from one another. Right? They flip back and forth. Quick, fast, and in a hurry. To quote Damon Wayans in what's the name of that movie? Where he played the Marine sergeant. Has it been 2 weeks since I killed anybody? So Yeah, he's going to do something quick, fast, and in a hurry. Let me show you a little trick to take your mind off the pain. So he breaks his finger. Um, so at room temperature, we're only going to get one signal because they rapidly interconvert. Now, if our detection speed was faster, then we might be able to see the difference between the two. But we typically can't see the difference between equatorial and equatorial, axial and equatorial hydrogens. If we decrease the temperature, though, then the signals, they don't interconvert fast enough. So if we conducted this NMR at, say, minus 100 degrees Celsius, we might be able to see the difference. It might split the peak for us. All right. So here we have two unique hydrogens. We've already looked at this molecule. The one closest to the oxygens is going to be shifted way, way, way downfield. And then the methyl hydrogens are going to be close to the reference peak. Now, I see a little blip there at about 7.2. I'm not sure what that is. And I see some other small peaks in there. So for now, we're drawing your attention to the major peaks. Now, I will point this out. Notice the magnitude of the peaks. The methyl group hydrogens have a huge peak, and the carboxylic acid hydrogen has a very small peak. The difference between those two is largely due to the number of hydrogens. So if you have more hydrogens that are identical to one another, you're going to get a bigger peak. And actually, with the output of most NMR spectra, they will tell you what's the proportion of one hydrogen at one peak relative to the hydrogens at other peaks. Right? And then that also helps you determine connectivity. Okay. So here we have chemical shifts for the different types of hydrogens. And they can vary a lot, right? Especially for the amines and the hydroxyl hydrogens. It all depends on what's attached to them on the other side. We just keep going. We're shifting further downfield as we add more shielding. Okay. So there's a distinction between the applied magnetic field and the effective magnetic field. The effective magnetic field decreases with the amount of shielding, deshielding, excuse me. The amount of shielding decreases the strength of the effective magnetic field. So that's why, and if you shield a proton with electron density around it, then it takes more energy to promote it to the higher energy state. That's the concept behind shielding. All right. Okay. Wish I could figure out how to fix that. All right, I may have told you the wrong thing. Let's see. The chemical shift of a proton will increase as the extent of de-shielding increases. Oh. Yeah, I did tell you wrong. When you increase the electron density around an atom, you shield it from all right. I think there's a semantic problem here. Let me go through it. Let me just read through it. Characteristic chemical shift of each type of proton felt by a particular proton depends on the extent to which the proton is shielded by the surrounding electrons. If the extent of shielding for the proton is decreased, meaning that the proton is de-shielded, then the effective field increases. An increase in effective magnetic field causes an increase in the energy separation between the alpha and beta spin states. That is, the excited versus the unexcited. So a proton will absorb a higher frequency photon and the chemical shift will increase. The chemical shift of a proton will increase as the extent of de-shielding increases. That means it's shifted to the left. As it's de-shielded. The more de-shielded a proton is, the more positive chemical shift farther to the left in the spectrum, the more the signal is said to be shifted downfield. All right, so downfield is to the left, upfield is to the right. And I know we got those spectra correct. So what they're saying is if the lone pairs like from the oxygen are near the hydrogen, it is de-shielding the proton. You know, that doesn't make any sense. I think it's a semantic problem. The less de-shielded a proton is, okay, less de-shielding is more shielded. The more the signal is said to be shifted upfield. Shifting to the left is downfield. Can you make sense of that? It just, at one time it made sense to me and now it doesn't. Okay, a proton will absorb higher frequency photons and the chemical shift will increase. So what does that mean in practical terms? Let's go back, or maybe we need to go forward. Yeah, let's go forward and maybe that'll help. Okay, a proton's signal is shifted downfield to a higher chemical shift value that is to the left, downfield's to the left. All right, here we go. Well, there's our zero. This is downfield. This is upfield. All right. And it's shifted downfield by more electronegative atoms. This downfield shift occurs because electronegative atoms are inductively electron withdrawing Okay. So this downfield shift is deshielding. One way it's deshielded is by electronegative atoms, like oxygens, like nitrogens, like halogens. They are deshielding the proton, which increases the effective magnetic field. So to this direction is we're increasing effective magnetic field. Deshielding is to the left. And the first effect is the nearby electronegative atoms, which are withdrawing electron density away. Okay, I had it backwards. Does everybody see where I made my mistake? Yeah, I had it backwards. The electronegativity of the atom is what's important. It's drawing electron density away from the hydrogens nearby and deshielding them, which increases the effective magnetic field. Because as long as you've got the electron density around that proton, you're shielding it from the strong magnetic field that you're trying to induce around that proton. Okay. That means that it's going to take more energy since it's in a higher magnetic field, and this magnet's in this magnetic field here. It's going to take more energy to get it up here. This is deshielding. Whereas if it's more shielded, then it will be, this is shielded. It will take less energy and the shift would be less. It takes less energy to get it to this state if it's shielded. Okay, so the first thing to consider is nearby electronegative atoms. And what we're showing here is a comparison between an unsubstituted and a substituted alkane. Right? If we just have carbons around that hydrogen, we get a shift of 0.9, which is very little. It's more shielded. Whereas if we put a fluorine in there, it's drawing electron density away from that hydrogen and reducing its shielding, making the effective magnetic field higher. That means it takes more energy to promote the nucleus to a higher state, and then when it relaxes, it gives up a stronger signal. Okay, I've got it straight in my mind. Are you comfortable with it? Okay. Okay, the other effect, magnetic anisotropy. We have to define our terms here. What is magnetic anisotropy? Anisos is from unequal and tropos means way. So it's an unequal way, right? Literally. Refers to the characteristic that is directional dependent. So we have a non-uniform magnetic field. That is, the molecule itself is inducing a magnetic field. Okay, what molecule are we looking at here? Benzene. That's benzene. It's inducing a magnetic field that is causing those hydrogens to feel an additional magnetic field. The external field is going one direction, and the induced magnetic field in that molecule is causing those hydrogens to feel a stronger magnetic field. Now, if the hydrogens were, this would be stupid, but if they were on the inside of the molecule, they would have a reduced magnetic field. Or if they were, say, on top or bottom, they would have a reduced magnetic field. But since they're out there in the magnetic field that is in the same direction as the applied magnetic field, they feel a stronger field. So what that does is, since they feel a stronger magnetic field, an increased magnetic field, their shift is further downfield. So you're going to see hydrogens that are attached, that are part of aromatic systems. And this benzene is just one example, but hydrogens that are in aromatic systems, they're going to give you a downfield shift, a very large downfield shift. All right, benzene itself is 7.3. Protons attached to carbon-carbon double bonds, like hex-3-ene, they will have a chemical shift that's large, but not as large as aromatics. All right. Let's see. All right. So we've covered that topic already. That just further explains. Okay. So we're de-shielding those protons as a result of the induced magnetic field in the either in an aromatic, or you can also see that in pi bonds. All right. Alkene hydrogens, how do we explain that one? They are also de-shielded by this anisotropy. So what that also tells us is that if it's just this molecule the way it is, we're going to see those hydrogens on this ethene molecule are going to be they're going to be de-shielded, but they're going to be identical because there's nothing else attached to them. We can explain the chemical shift only by this anisotropy. All right. Alkynes. Let's see. Alkynes. We would expect the alkyne hydrogen to have a high chemical shift, but they don't. The reason is they're not affected by the induced magnetic field of an alkyne, simply because of their geometry. Right? With an alkene, you've got those hydrogens sticking, they're sticking out there in the induced magnetic field, so they are affected. But an alkyne, this is a linear molecule. Those hydrogens are not affected by the magnetic field lines of the electrons in the pi bonds. So their chemical shifts are relatively low. Their chemical shifts, I think, now it doesn't say that, but I think it's based upon the induced electronegativity of the triple bonded carbons. Right? They will give you some induced electronegative withdrawing effect, which will slightly de-shield those hydrogens. That gives them some chemical shift, but not as much as you see with the alkenes. Okay. An alkyne protons lie where the local magnetic field opposes, which results in a shielding effect, not a de-shielding effect. Well, I wouldn't say so much that. Shielding and de-shielding is relative term. Right, that's the way I look at it. We can say large de-shielding if it's way, way over here. But when you say there's a shielding effect, compared to what? Right? Compared to zero? If it's compared to zero, then the de-shielding would have to be on the other side. And we've chosen our reference standard to be completely inert in terms of magnetic field. Okay. I'm not sure how much this is going to help. How do we deal with protons and molecules that don't closely match the ones in the table? Well, they're in a range, right? That's for sure. We would expect this methyl group hydrogen to have very little chemical shift, whereas the electronegativity of chlorine would give it more shift. Two chlorines would give it even more shift. So we're more de-shielding of the hydrogens. But also, not only that, the number of hydrogens that are in the vicinity that are attached to that carbon will also determine the magnitude of the peak. Now, we haven't talked about that yet. I mean, I think Carty is putting that too late in the discussion. I think that should have been up front, but there it is. The effects that cause de-shielding are essentially additive. So if you have more than one effect, de-shielding, then you can typically sort of add them up, right? The difference between 0.9 and 3.1 is 2.2. And if we add 2.2 to 3.1, we get 5.3. So that's additive. The additive effect of two chlorines versus one. Okay. How about de-shielding effects and distance? All right. Yeah, that hydrogen that's very close to the benzene ring is going to be the most de-shielded. So it'll have the largest chemical shift, 7.2 in this case. Right. The number one carbon with that hydrogen be less of a shift. And once you get two carbons away, then you essentially have almost no de-shielding at all. All right, I said all that already. Okay. Chloromethylbenzene. All right, if you start with 0.9 as an alkane hydrogen, and then you say what's close to it. Well, if it's only once removed from a benzene ring, we would say the effect would be about 1.4. So if we go back to the one here, the effect there is 2.6. 2.6 and 1.4 and 0.9 would be a certain effect. But now we have a chlorine on the other side. So that effect is roughly 2 parts per million. So we should expect to see something in the neighborhood of 4.5 for that, for the hydrogens attached to that carbon. Okay. And our estimate is pretty close. The measured effect is 4.6. We estimated 4.5. All right. I'm not going to, I wonder if I have any of these examples in the sample test. Well, let's take a quick look. Because I don't want to waste your time on doing something that I think there's a better way to approach estimating chemical shifts. And that's just to have regions. And once you have regions, then you can differentiate between the various peaks and the unique hydrogens in your molecule, rather than going to all the trouble of trying to estimate these chemical shifts. I mean, I'm sure it's a valid technique, but it seems to me it would take an awful lot of time to master this technique, and with very little return. So I'm not going to spend a lot of time on this one either. This is mathematical derivation of the NMR signals. And I think this is the expression that I grew up with is too much sugar for a dime. I don't know if they still use that anymore. Right. This, you don't have to know how to use this, but this is an expression of why is it called ppm, parts per million. Right. This is new. This is the frequency of the sample minus the frequency of the tetramethylsilane over the frequency of the what's OP? Oh, apply the frequency of the signal applied to the sample. So that's how you get the magnetic shift. All right, what about deuterated samples? We put those in there. That's the solvent. And we use deuterated because it produces a signal that can be recognized as not part of the sample. Most of the sample is going to be solvent, right, that you put in the solution. All right, so we put in the deuterated sample, and it gives us a peak at a different frequency. Okay, we've already described that. I'm not going to spend. I think I'll leave that up there for now. All right, now we're going to talk about sample integration, signal integration. In Carty's description here, we've got a superimposed line that goes across the graph. And you'll notice there that as it crosses the peak, this is integrating the sample. So as it crosses the peak, this integration of the sample goes up right there until it finishes the peak, and then it levels off again. So that integration tells us the difference between where it started and where it ended is an indication of the number of hydrogens in the sample. So it integrates the peak. Now, other outputs from NMR spectra, instead of having this superimposed integration signal, will simply put a number in parentheses over the peak. And then the ratio of those numbers gives you the ratio of hydrogens in the sample. And that, when you look at that, if you go and look at that chem historian video, that's the way that he approaches it. The type of NMRs that his equipment produces gives you those numbers. And I think that's more useful than trying to read these integration peaks, integration signals, excuse me. So here we see this size integration represents 4 protons. This one represents 6. And you can see the relative difference in size between the two. That's why I say that the number above the peak would be much, much more useful and get you there quicker. Because this way you have to actually like estimate the size of the integration and ratio it with the others. Let's see. Now I'm not sure if let me look at the sample test again and see how it's presented there, if it is presented there. Because we're not just covering NMR in this one, right? This is going to be NMR and UV viz. And exam 4 is aromaticity and mass spec. All right. All right. We don't get into that much detail. Okay. So I'm not going to hammer that one too hard. Now we can get into the concept of peak splitting. If you have hydrogens that are unique, say in that example, the hydrogens on the 2 are different than the hydrogens on the 1 carbon, then you're going to get 2 separate, we're going to get 2 peaks, locations, different shifts. But as it turns out, the peaks at 4, that's a doublet, and the peak at 5.8 in that neighborhood is a triplet. The reason for that is that the hydrogens that are on adjacent carbons have an effect on the shielding and deshielding of the neighboring hydrogens. So if you've got 1 hydrogen on the carbon 1, but 2 on carbon 2, 2 hydrogens are going to produce 2 valleys. I look at it that way. 2 valleys means 3 peaks. Okay? 1 hydrogen means 1 valley. That's 2 peaks. Does that make sense? I mean, that helps me rationalize it. So you get a doublet when there's 1 neighboring hydrogen. You get a triplet when there are 2 neighboring hydrogens. If we had 3 neighboring hydrogens, then the next door carbon, its hydrogen would be split 4 ways. And anything above that, I think, is called a multiplet. Now, what if you had, let's say, here we only have 2 carbons. What if we had 3 carbons? And the 3rd carbon had hydrogens on it. Well, the carbon in the middle would have a hydrogen with how many neighboring hydrogens? Well, it could have 2 on one and 3 on the other, which would be 5 valleys or a sextuplet. Or we might call that a multiplet. Okay. This is known as spin coupling. Spin coupling alters the shielding effect for each of the hydrogens and gives you a split the signal. Excuse me. Now, the relative heights within that split can be described by Pascal's triangle. Everybody know Pascal's triangle? Where you put 1 here, and then 1 there, and then 1 plus 1 is, let's see, 1 here, 1 plus 1 is 2, and then 1 here. And then this one is 1, this one is 3, this one's 3, and this one's 1. And this one's 1, 4, 6, 4, and 1. So you just keep going with that progression, adding these two to give you that one. Adding these two, this would be like 1, 5, 10, 10, 5, and 1. And what you see is with a, this would be the relative heights of the peaks for a quintet. Okay, so how many equivalent protons do we have in this molecule? Well, the ones that are on the ring, on the aromatic ring, are experiencing the same de-shielding effect that we see for anisotropy. All right, so those four are going to be identical. And the methyl, actually, this is a paraxylene, right? Two methyl groups on a benzene ring. 1,4-dimethylbenzene, which is xylene. One type of xylene. There are three types of xylene. If you buy it in the hardware store, a can of xylene, it's going to be a mixture. The meta, the ortho, the meta, and the para isomers. Okay, relative height, so we see that the integration there, and we should have numbers here, like the ratio of the one around 7 and the one around 2 1/4. The ratio should be 2 to 4. Actually, why didn't those peaks show splits? Oh, okay. Why didn't they show splits? Well, first of all, the methyl groups are 2 carbons away, so they're not going to have any effect on the benzene hydrogens, the benzene ring hydrogens. And for the same reason, those identical hydrogens on the benzene ring are not going to affect the methyl group hydrogens because they're 2 carbons away. The splitting only occurs when the hydrogens are 1 carbon away from each other. All right. So these two peaks are going to be singlets. They have no neighboring unique hydrogens. All right. What's the N+1 rule? Well, simply stated, the N+1 rule is if you have, say, a carbon like this and a carbon like this, let's say like that, the peak for this one is going to be the same, different than the peaks for these three right here. So what's going to happen to, this is only 1 carbon away. So what's going to happen to this peak? It's going to be split into N, 1, 2, 3, plus 1. So this one's going to be a quartet. And this one is N+1 is going to be a doublet. That's all that means. How many N is how many neighboring hydrogens, add 1, and that's how many you got. Now let's see if it's going to make me a liar. Let's see. Doublet, okay. So we have 2 neighboring hydrogens plus 1 is 3. It's going to make a triplet. Okay. What Dr. Carty is trying to do is explain why these appear. Right. So you can have those hydrogens can have, both of them can be in the same direction, or they can be in the opposite direction, spin, or they can be one way and one the other way. And that gives you a higher peak. I would just remember the n+1 rule, right? Or, right, if you have 3 neighboring hydrogens, that's 3 troughs, means 4 peaks, right? The only way you can get 3 troughs is to have 4 peaks. I like that one better. I'm sticking with it. All right. We're not going to spend a lot of time on that. Oh, there's your Pascal's triangle. And that's trying to explain the ratio of heights of your split peaks. All right. How about what happens to OH and NH protons? OH and NH protons often do not exhibit coupling. Let's see why. Rather than coupling, they give broad singlets and do not appear to couple with adjacent hydrogen. So in that that amine, that ethenamine, you get coupling with the hydrogens, but the with the carbon hydrogens, but not with the nitrogen hydrogen. The amine hydrogens don't couple. Those hydrogens, rather than being coupled, give you just a broad peak. And the explanation there is rapid proton exchange. Rapid proton exchange with what? The solvent? They undergo extensive hydrogen bonding and can hop from one nitrogen or oxygen atom to another. Okay. So the sample molecules that are in the magnetic field, because of the nature of oxygen and hydrogen, can swap hydrogens among molecules. And what that tends to do is muddy the water. That's the way I look at it. It just muddies the water, broadens the peak, and you don't get unique splitting. So if we look for those peaks, that's an indication that we do have nitrogen or oxygen because of the hydrogen bonding effect. They average out the environment. That's another way of looking at it. And yes, I already said that. We can take advantage of this to identify OH and NH signals. Now, how do you tell if it's an OH or an NH signal if you find one of those broad peaks? Well, you look at the molecular formula. If you're lucky and the molecular formula only has nitrogen in it, then you got it fixed. If it's only got oxygen in it, fine. If you have nitrogen and oxygen, then you might be screwed. Unless you get a different shift for each one. The nitrogen shifts one, the hydrogens shift one, oxygen shift another, or you go to nitrogen NMR or oxygen NMR. And that may be required. If you're doing a research project for your major professor, then you may be required to do that because he's too busy. She or she's too busy publishing papers and hunting down grants. Right? They can't go in the lab. I had a professor like that. We called him the editor because he sat in his office all day long typing out publications. Right? Never came. The only time he came in the lab was just to FaceTime. So, so we were essentially on our own. He never went to the field either. That was from a master's degree. Huh? Yeah, right. And I guess we sort of appreciated it because he never got in our hair. Um, let's see. Let's see. If a sample is treated with deuterium oxide, which is the deuterated form of water, the OH and NH protons in that sample are rapidly replaced by deuterium, whose signal does not appear in the NMR spectrum. Thus, the intensity of OH and NH signals decrease dramatically and disappear entirely. Oh, that's a good trick. Yeah. Just add um, deuterium oxide to your sample, and if the signal disappears, then you can identify that broad peak as either OH or NH signals, but that doesn't differentiate OH from NH. So still, you might have to go to other methodologies to determine which is which, if they're both in the same sample. All right. Now the video that I want you to look at doesn't talk about this one, the coupling constant. Each peak in a split signal represents a slightly different frequency being detected. So the frequency difference between any pair of adjacent peaks in a split signal is called the coupling constant, which is usually in values of hertz. And they're usually, the values are unique for unique protons that are involved in the coupling. Here are some coupling constants that are given. If you have the relationship between the protons are simply, oh, that's interesting. That second one down. If the hydrogens are 2 carbons away, you don't get a coupling constant because it doesn't produce a split. If the hydrogens are attached to an alkene, then the coupling constant is very large, between 7 and 12. If they're cis, if they're trans to each other, it's even larger. That's interesting. If they're on the same carbon, then why would they be? If they're on the same carbon, why would they have a coupling constant at all? There would have to be, that one escapes me. The rest of them make sense. But when you've got 2 carbons, okay, if for that center one there, where you've got 2 hydrogens on the same carbon, if those hydrogens are unique, if they're different from one another, say you had a chlorine in the cis position to one and trans to the other, then they would be unique hydrogens and would produce a doublet in one and the other. Then the coupling constant would be valid, but only if those 2 hydrogens are unique. If they're the same hydrogen, the same shift, the same downfield shift, then you're not going to get a coupling out of those 2. Now, I don't think he said anything about that one. He just slapped those values up there and assumed that we'd figure it out, I guess. Okay. So coupling constants can be used to interpret the spectra if you are mindful of the following. signals of protons that are coupled together exhibit the same coupling constant. So if you have two unique hydrogens that are split and the coupling constants are identical, then they must be on adjacent carbons. And let's see, and number 2, long range coupling, 17.4 long range coupling. Is that the next page? No, it must be the previous one. Yeah. Long range coupling. Oh. So we didn't attack these on the far right. So they're telling us that those hydrogens on that benzene ring can split each other's signals. But the way they're presented, those are identical hydrogens. How would they split? I don't see how that would happen, right? Those are meta in the middle and para in the bottom and ortho in the top. I'm sorry, it doesn't make any sense to me. We're splitting signals with coupling that I didn't know existed. Now, here we do have A, B, and C are unique, right? Because of that bromine, right? Now, that makes sense. But if they're coupled to more than one, how does that affect the signal? Say we have C is coupled to B and A. All right, and B and A are unique. So that would be 2 plus 1 is 3. It should be a triplet. But it looks like we've got a quartet instead. 1, 2, 3. All right. This is known as complex splitting. Okay. I'm not going to throw any complex splitting at you guys. I don't think that would be outside the realm of the course. I mean, it's interesting to know about it, but complex splitting is not going to be an item for your mastery. Okay, this might be more useful though. Well, actually, this is more of the complex splitting. All right. An example of splitting diagram for the B proton is at 5.97. The first splitting, okay, hold on a second. Let me get that out of the way so I can see what I'm doing. Okay. All right. More of the same. I'm not going to hold you to that one either. Just recognize that it does occur. So here we have a triplet of doublets. This might be easier to understand. And you know, the NMR spectrum, like any instrument, the more money you pay, the better quality output. Right? So if you want to be able to detect these very complex splittings, you're going to have a very expensive piece of equipment that will give you the resolution that's required to see that complex splitting. Otherwise, you may miss it altogether. Right? If you're using a student model, then it may not give you the resolution you need to see those complex splitting patterns. Okay, the signal for carbon-2 is the one we're focusing on. So how many carbons do we have in that region? Well, we've got one on the right attached to the carbonyl carbon, and then we've got 2 on the left. right? So we would expect to have a triplet split for the one on the left, because there are two hydrogens, and a doublet split on the one on the right. So what you have is a triplet of doublets. Right? I misspoke earlier when I said you would, looking on both sides, what you would actually have is you would go to here's the way I'm thinking. You go to the one that gives you the most number of splits. So we go to the left, right? Two carbons, two hydrogens gives us a triplet. And then the one on the right splits the triplet into doublets. Okay, that's the way I look at it. Right, so this is a very complex one on the right here with this hexane 3-one. We're taking the methyl group hydrogens and splitting them 1, 2, 3, 4, 5 ways. All right, we're not going to go into that much detail. So let's, how would you get around this? Well, sometimes you just change don't change the magnetic field, but change the frequency of the signal. Right? In 90 megahertz spectrometer and 300 megahertz spectrometer give you different outputs. So I think this one is a 90 megahertz spectrum. Yes. And the next page gives you the 300 megahertz. The 300 megahertz gives you a more resolved spectrum. Two distinct triplets are shown. Whereas with the 90 megahertz, you get this mess. So with 300 megahertz, you get a doublet of triplets. Now, it's better resolved as the magnet of the spectrometer becomes more powerful. But the 300 megahertz, that's the imposed radio signal, isn't it? Yeah. That's the imposed radio signal rather than, or is it 90 megahertz pulsing of the magnetic field? That doesn't make any sense. No, it has to be the radio signal. I'm not sure how Carty gets better resolved as the magnet of the spectrometer becomes more powerful. Well, sure. If it has a more powerful magnet, then maybe you do need a higher frequency signal, right? That's the only way that makes sense. At least with the information that's given. All right, how does it depend on magnetic strength? Okay, say we have a different, a more powerful magnet. How does the magnet affect it? Okay, figure A, two unresolved signals are plotted with frequencies on the x-axis, all right? Then we increase the strength of the magnet, and now we get a resolved doublet of triplets. So when the signal width becomes narrower with stronger magnets. And that adds to the resolution. All right, now we're going to shift. We've been talking about hydrogen NMRs, or proton NMRs up to this point. Now we're going to talk just a little bit about carbon-13 NMRs. And the concepts are basically the same, except that there are complications, so to speak, that make the carbon-13 NMRs less useful. I mean, if you have to pick, go with the hydrogen. But if you have the carbon-13 available, it might offer some advantages. One disadvantage is that because the abundance of carbon-13 is so much lower, right? It's only 1.1%, you get a weaker signal. So the top trace shows you a very noisy baseline. Okay. The problem with that is you can't pick out weak signals reliably. So the way around that is to signal average. You may go thousands of repeated measurements on that same sample. And in the process, you reduce the baseline signal noise. So the second one, that the B, is the signal averaging for several thousand repeated measurements of the same sample. And you pick out signals that were almost indistinguishable in the first measurement. Okay. Average large number spectra. Okay, I've done that already. Talked about that. Okay, and these, what you're looking for is distinct carbons, right? For the same reason that we looked at distinct hydrogens, we're looking at distinct carbons, and each distinct carbon is going to give a separate signal, a different downfield shift from the tetramethylsilane reference point. All right. Solvent effects. You still get a solvent effect because the deuterated trichloromethane has carbon in it. Right? Some of those carbons are going to be carbon-13s. But how about the environment? The environment is different, right? It has 3 chlorines, but it also has a deuterium atom in there. So that should shift the solvent peak slightly so you can pick it up. And that's where we see in this, the B trace down here, you see pointing toward the trichloromethane signal. All right. That we do get coupling, like we did with the hydrogens. We do get coupling between adjacent carbon-13 atoms. The same way we did with protons. But we generally don't observe signal splitting like we do with hydrogens. And that's simply an artifact of, well, 2 things, is the environment of the signal that's being picked up. And if we have to average thousands of measurements to get a viable spectrum, that sort of washes out the splitting that would have taken place anyway. Plus the fact that we have such a small amount of carbon-13 that they don't affect one another as much. So we typically don't see carbon splitting, even with high resolution spectrometers. Let's see. And we might expect to see coupling between the carbon-13s and neighboring protons. Broadband decoupling is responsible for that one. It's a procedure that sends a specific range of RF radiation through the sample, forcing all the protons to flip back and forth rapidly. So if the protons are flipping back and forth rapidly, they don't contribute to the signal output. So we can focus our attention on just the carbons. All right. Well, I wouldn't worry too much about the fact that this technique washes out the protons, so we don't see where the protons are attached to the carbons, because we typically don't want to see in a carbon-13 NMR spectrum, we don't want to see hydrogens, but that's the whole purpose of doing the carbon spectrum. So we would do a separate spectrum for the hydrogens, and then we compare the two if we needed to further confirm a particular structure. Now, what's this DEPT spectroscopy? Let's see. All right. Well, we have these are typical shifts for the different carbons. And we see these are larger values, right? But the scale of the spectrum is also compressed so that we can incorporate these shifts. Right. So the relative values for the shifts are don't compare them with hydrogen shifts. Right. There's different values. Okay, so I guess we're going to talk about DPT, not DP. I forgot what it called now. DEPT. We're going to cover that in just a second. See if it has value for us. So here's a typical spectrum for this particular molecule. This would be 1, 2, 3, 4 is the, let's see, 4. I'm trying to remember my nomenclature now. Longest chain would be 1, 2, 3, 4, but it has to include the carbonyl group. So that'd be pentanal. It would be 1, 2. It would be 2-methyl pentanal. So this is the carbon-13 spectrum for that one. And the area under the peak is not proportional to the number of carbon atoms contributing to that peak. So that's one of the disadvantages of this method, is now we can't tell how many carbons are represented by the peaks. And we're talking broadband decoupling again. All right, nuclear Oberhauser effect. If you're not going to be an organic chemist, what does it matter? Just remember that carbon-13 NMR signals, you cannot assign numbers of carbons to the area under the curve, whereas with hydrogen NMR, you can. All right. We can construct, okay, now we're going to get to DEPT. I'm not sure what that stands for yet. Here it is. Distortionless enhancement by polarization transfer. So this is a modification to the carbon-13 NMR spectroscopy, and it's obtained by superimposing a specific sequence of RF radiation pulses applied to the sample, and that gives us a more useful spectrum. Let's just put it that way. Now, this produces a spectrum in which the signal given off by the carbon-13s depend on the number of protons attached to those carbons. So now we can identify both the shift of the carbon and based upon the hydrogens that are attached to it. So the illustration here is with this, let's see, ethyl benzene. And we see that we have a methyl group there that has that carbon is attached to 3 hydrogens. Then we shift to 26. That one's attached to 2 hydrogens. And then we get 3 peaks with individual hydrogens. And there's a carbon with no hydrogens. So that does give us a little bit more information that can be used for structural analysis. Cozy spectrum? Cozy spectrum. All right, what's a cozy? That's a different method. It looks like a 2-dimensional method. NMR spectra can also provide a variety of 2-dimensional spectra. All right. So are we interested now? Are we going back to hydrogens? Okay, so what's on one axis? One axis has we're back to hydrogens. A hydrogen chemical shift and another hydrogen chemical shift. All right. They have one frequency axis on the X and a second one at a different frequency. Right? Come on, here we go. So 2 frequencies are used. So we're exciting the molecule in the magnetic field with 2 different frequencies, and we're getting an output. And I assume that the computer algorithm is required to parse out all the information that's coming from your sample in order to make sense of it. So we got 2 different frequencies, and if we identify the carbon C, that N methyl group on the right, so with one frequency, we're giving a chemical shift of 1.3 or 1.2. And with the other frequency, we're giving a chemical shift of 1.2. All right, so that doesn't change any. How about B? B gives a chemical shift of a little over 1 with one frequency and over 4 with another frequency. So that tells us that, oh, okay, that makes perfect sense. The methyl group for C, those hydrogens are giving us a shift, the same shift for both frequencies, right? Because they're on the end of the molecule and they're only adjacent to one other carbon with its hydrogens. Okay. A, on the other hand, those hydrogens are adjacent to a carbonyl. So A should give us, let's see, a shift of 2 and 2. They're identical. They should give us the same shift. But the B hydrogens have C hydrogens on the one side and an oxygen on the other side. So they're going to give us different shifts. Okay, I see the advantage now. So one common type of spectrum comes from homonuclear correlation spectroscopy. That's what we're talking about here. And if we draw a diagonal across called the cross peaks, so we're going from C to A to B. The vertical arrow corresponds to the protons that produce signals C1.3, and the horizontal arrow corresponds to protons that produce signal B4.1. All right. I'm sure we could get into the weeds with this, but what I'm taking away is the different superimposed radio frequencies, the two different frequencies, give us two different responses if the hydrogens are neighbored by hydrogens on one side and different atoms on the other side. So this is just added information to help us determine the structure of the molecule. All right, what are we saying? B and C protons are coupled. B and C are coupled, yeah? Okay. Okay, that's why they drew that diagonal line. It goes from 0 to 5. Diagonal line says that B and C are coupled. The peaks that appear off the diagonal, called cross peaks, indicate which protons are coupled, indicated by the thick red arrows. All right. Don't worry about that. I think we've derived everything we need to from this one so far. Het core is another way. What do we do with het core? Heteronuclear correlation spectroscopy. All right, so the one-dimensional spectrum is X and Y axis. This two-dimensional spectrum, het core, each cross peak provides information about which protons are attached to which carbons. All right, so we got, the homonuclear, the previous one. Okay, here we go. COSY is homonuclear. In other words, we've got hydrogens that are being exposed to two different radio frequencies, giving us two different responses. Okay, now we're going to pick up signals from hydrogens and plot them against carbons. All right. So what does that tell us? The thick red arrows indicate that the carbons that produce signal E in the carbon spectrum are the vertical arrow, and they're attached to protons that produce signal E in the proton spectrum. Oh, I see. Okay, so we're on the x-axis here, we're superimposing the NMR spectrum for the carbons, and the NMR spectrum on the x-axis, or the y-axis, excuse me, is the spectra for the hydrogens. And where we get a signal that's assigned to, that's occurring where we have the quartet on the hydrogen and the signal for the carbon, that says that they are coupled. Okay, so that's what those red arrows are showing us. This value here is showing that the hydrogens and the carbons are coupled at that. So the E's carbons have the E hydrogens. And that makes sense because the F is a methyl group, which means the E hydrogens are going to be split 4 ways. That's about all we need to take away from that one. Okay. All right. I'm not going to hammer this one too much. I think, to be honest with you, if you view that video, that Englishman is going to clear a whole lot of things up. It's going to take all this mishmash that we've covered today, and it's going to make a whole lot more sense out of it. I think that would be very helpful. Not that you have to, but I suggest. Take 20 minutes and watch that video. Okay. And I put these up here simply as guides. So this is one signal. This is one spectrum that can be interpreted. And this is hydrogen NMR. And actually, when you have in front of you an NMR spectrum, I would, for each one of the peaks, I would pencil in what you know about that peak. Right? How many ways is it split? Say there's a carbon with hydrogens on it. Say if it's split into a triplet, that means the neighboring carbon has to have 2 hydrogens, and then that will help you see whether or not one shifted peaks correlates with another one. Like if you have 2 peaks, for example, say you have let's say a triplet here, and then over here you have a double, like that. There may be other peaks in there, but the hydrogens attached to this carbon versus the hydrogens attached to this carbon, if these are coupled, then this one is experiencing that doublet to make this split. So this one has to have only 1 hydrogen, whereas this one is split. No, this one has 1 hydrogen. This one has to have 2 hydrogens to split this one into 2. So if these are coupled, then you can see that this one splits that one, and this one splits that one. Okay. Putting the pieces together. All right, we can dispense with that. For carbon NMR signals, determine the number of carbon signals, right? That tells you how many unique carbons are in it. That's the major takeaway from a carbon NMR spectrum. The number of signals gives you the number of unique carbons in the sample. And then you'll have access to ranges, right? So you can look at the shifts and say, this is probably that type of carbon versus another type of carbon. And then you may even be able to combine IR spectrum with NMR spectrum. So if this unknown has a molecular formula of C5H12O, then you know the O could be what? What could we have for O? We could have a carbonyl. We could have only 1 O. That means it could be a ketone, or it could be an alcohol, right? So you look at the IR spectrum and see, All right, what type of oxygen is it? Looks like it's an alcohol, right? With that broad peak at about 3,300, 3,350 maybe. So we got three signals. That means three unique carbons, right? They're their positions. There are 5 carbons in that sample, but there are only 3 unique types of carbons. So what are the possibilities? Well, we look at the positions and we find that the least shifted, probably the CH3 group, and then there may be a CH2 group, and then one carbon has no hydrogens. All right. That's enough.